Hey everybody, this is Larry, this is me going with Q2, and you can see that I struggle a lot with this one. Minimum speed to arrive on time. So this one, conceptually, is not that hard. But for me, I had issues with precision. I think, to be honest, if they're going to do something like all these weird hour stuff with 2 digits after the decimal, they should have just given you a string so that you can parse it better. Because if they give you in a float, it's going to always be a little bit off, or like it's not. You don't get to choose the position. So this one's a little bit awkward for that reason. But the way that I did do it very quick. I did okay time. It's just by binary search. The idea is that ignoring the precision problems, which I'm not going to go over that much because precision problems can go beyond the scope of whatever. So you have to really precision problems are hard. It's beyond my ability to teach, I think, because it's just one thing that I avoid as much as I can, which is why I think that the input should not be a flow. But going back a second on binary search, the idea is that, okay, you have some speed function, right? So the thing is that obviously, so there are two things that make it monotonic, so that you could do a binary search, which is that, okay, given a certain speed, if speed works, then speed plus 1 works, and etc., right? Speed plus 2 works, and so forth, right? So that's all you need to do, and just based on this, that's all you need, right? Because that means that you kind of plot out the true force thing. You get force. Oops. You have force, true, right? And and these are discrete speed, and now you're trying to find the minimum speed for which this is true. So you're trying to find the first true, if you will. So basically, you're looking for this thing, and then your function is just implement what they tell you, right? To calculate whether this speed is good, you just do for x. For each distance, you do the time, you round up because the bus or train, whatever it is, the train leaves only at the hour. So if you go over the hour, you just keep going, right? And then that's pretty much it. So you round up, and then at the end you do some math on whether the last part of the trip, whether that is that fits you into the fraction part of it. There's some precision issue here, as I mentioned, I'm not going to get into, but this is pretty much how because basically this is just hour. We check whether the fraction part of hour is bigger than x minus speed, which because x is the distance, and of course that means that you multiply speed on both sides to get this thing. Again, precision errors aside, that's basically it. So on the binary search, you go, okay. So the way that I always think about it, instead of memorizing patterns, is I go, okay, there are only 2 scenarios, right? So that given this function, it could either give you a false value or a true value. If this is a false value, then what happens? That means that everything to because we're looking for a true, that means that this value is eliminated, and everything to the left of this value is eliminated, meaning that the left will have to be on the next value. So that's basically how I write. If this is not good, then left is mid plus 1. And then the only other possibility is that, and I guess I forgot to mention this, is that I use this inclusive range, because the reason is that if left is equal to right and it is inclusive, that means that your answer is on the left or the right, because they're the same number. But in any case, the other case is that if this is true, then that everything to the right is no good, because this is, your maximum answer is already, this is already an answer that you can return. So everything to the right of it, we don't have to look up. So that means that we can eliminate everything to the right, meaning that we set the right to admit. So that's pretty much it. This is binary search. It's a very tricky problem. Yeah. So yeah. It's a very tricky problem because I spent like 8 minutes and a wrong answer on just the position, and even before that I had some weird off by ones or something. But hope you did well, and you could watch me solve it live in the contest next. Man, there's too much reading. We must travel. What an awkward problem. I don't even know that's enough position. This is good. Why is this not the third hour? This is a very awkwardly phrased problem. And no one has gotten it yet for that reason, even though it's a cute too. So if this is good, then we can try a smaller one. has to. And this is like really awkward, but especially the last. Why is this so awkward? And now this is our. Something like that. It is a very awkward problem. Oops. That should not be it. That's not even right. Well, now. Speed 1, I write force. Why did I write force? Because why is it force? Because at speed 1. Wow, this is not going well. But at speed 1. So this should be 4 for time. So that's 2. Hour is 2. Speed is 1. And x is equal to 2. Why is x 3? Oh man, I am dumb. Speed should not be 0, that's fair. Is that good enough? Okay. I don't know if this is right though, but what an awkward problem. Please. If it's too slow, I'm gonna be sad. Okay, wrong answer. Still sad. Why do I give 2.01? So my speed is. I hate you, but okay. So at 2.01. That's not make sense. Why am I off by 1? I mean, I know why I'm off by 1, but maybe there's a dumber way of doing it, to be honest. And I'm just being stupid. And that's why there's precision errors. Man, I'm really struggling on this model. This is mostly right, but it's such a weird, silly problem. So that's gonna be force, but why? Oh, because it's 1 over a million, or 1 over 10 million. Twice. How do I get? Is there a big float in here? Big float. I know 1/100 is in there. How do I handle this? This is this round up. So then hour is the number that they give you. This is so awkward. They give you, what's the input? 2.01. I mean, yeah, exactly, right? So this is so silly that they don't even. Is there an easy way to do this? A lot of people gotten it though. What am I doing wrong? I know what I'm doing wrong, but how do I do it in a way that isn't that? Oops. I mean, does that work? Nope. That is just so bad. I don't know how to solve this. Maybe. The position was us. Because this is minusing 1/1,000,000 at a time, but 1/1,000,000 is 2, whatever. Why don't they just give, if they give the thing in a string, then I could handle this much better. But I don't know how to solve this. Maybe. So why can't I just multiply this? It's very awkward. I got the concept like pretty quickly. It's just I don't know how to implement the thing in a good time. Like how do you resolve the worst case? I'm spending most of the time on this. Okay, fine. It seems like the worst answer is like what 10 million, but how do I fix this? Let me Is that good enough? I don't even know anymore. Probably still wrong, to be honest. Just such a hack. But now I don't know how to do it. Huh, okay, that's such a silly hack. So I don't. This is me again before the contest. I just forgot to talk about the complexity. This good function is going to be linear time, so this is O of n time. This function is going to be O of log u, where u is the size of the universe, which I took 10 to the 12, but I think 10 to the 9 is probably good as well, because that's just the hours. As a result, the entire complexity is just going to be O of n log u, and in terms of space, we don't use any extra space. So that's pretty much it. And you know, n is 10 to the 5th, and this is going to be roughly, you know, 20 or 30 or something like that. So yeah, this is going to be fast enough, and that's basically it. And now you can watch me solve it live in the contest next. Hey, yeah, thanks for watching. Hit the like button, hit the subscribe button, join me in Discord. Let me know how you did on this contest. I did okay, but yeah. And also on this problem, what do you feel about my solution? Yeah, you know, stay good, stay healthy, to good mental health, and I will see you later. Bye-bye.